Ferrario from the University of Pavia, and she will talk about stationary solutions of 2D fluids. Thank you very much.
So first of all, I would like to thank the organizers and the Newton Institute for support. Let me say something about starting with the talk. I will present some mathematical results, and I think the audience is a quite huge one about interesting research. So let us focus on statistical behavior. In the title, there are stationary solutions, the two words. We take a basic equation for fluids, even the easy model of two-dimensional fluids. And I will try to revise with you the basic results obtained by means of stochastic analysis. So the idea is, wait a moment, it was easy before. Put it here. Okay. What have you done? Okay.
Clicked on there.
So first, I will introduce Navier-Stokes equation with some stochasticity. Here, stochasticity means a stochastic forcing term, which is, let's say, of wide in time and with some regularity in space, something which allows, mathematically speaking, of allows to use Ito calculus. So stochastic Navier-Stokes equations are the easiest model, especially in two dimensions. Okay. Then I will present some results for a variation, which is Navier-Stokes with a fraction of this equation. And number one is our reference setting. Then we make some modification, and we can deal with the damped Euler equation with stochastic forcing term, number two, and the number three is a result about deterministic Euler without forcing term, and the aim is to find some result about the stationary solutions. So again, the statistical behavior. Statistical behavior appears in the Kolmogorov theory of turbulence, and so we need some, let's say, reference measure or some stationary process solving the equation, which allow to perform a statistical means. So Navier-Stokes is the system written there. Okay, that one. The unknowns are the velocity u, the pressure p, and we are given u, which is the kinematic viscosity, positive, a deterministic forcing term, and n, which is the noise. We will take the easiest model for the noise. We're supposed to work in a domain of dimension d, and we work for positive times, and we have to assign some initial velocity. We will see later. Problem can be considered in dimension 2 or dimension 3. Dimension 2 is well known, well studied. I think we can say in the stochastic setting, suppose that you take the noise, which is the derivative of the Wiener process, enough regular in space and white in time, so the noise. We call this one an additive noise. The equation has been studied since 20-25 years. Okay, and you can deal with a bounded domain, smooth enough with Dirichlet boundary condition, or the torus, which means a box with periodic boundary condition, or you can work in the whole plane and put also other spatial domains, and some results are available. Maybe the torus is not very interesting from a physical point of view, but the mathematical structure is much richer. So sometimes I will present some results on the torus. And if it's possible, we deal with, let's say, more physically interesting problem with a bounded smooth domain. Okay. We need the free spaces, which are the usual spaces. First, we deal with the divergence free spaces, which are smooth enough and which are zero on the boundary. We close with space with respect to L2, and we get the space H. we take H intersection H10 with a zero condition on the boundary, and we call this V, and V prime is the dual of V. And these are the spaces, and we denote by capital Q the covariance of the linear process. So it says how regular in space is the linear process. Okay? And you have a lot of results about sufficient conditions providing existence of a unique solution. Why unique? Because we are in dimension 2, okay? And this is the basic one. Initial data, which is of finite energy, fulfilling the divergence condition and the condition of the boundary. The forcing term, the deterministic one, which is a twin space in D prime. Q is trace class operator in H. There exists a unique solution, and the paths enjoy the same property, let's say, of the deterministic Navier-Stokes. So to add the stochastic forcing term does not change too much the mathematical analysis. What about stationary statistical description? We look for invariant measures. So first of all, we look at the evolution of a system through observables phi, and we take a mean. So we introduce this family of operators pt, we fix t, okay? This is a family of operators. We can show that this is indeed a semigroup, Markov semigroup. It acts on observables phi, but the dual acts on measures. And we say that a measure mu, think of a measure mu on the space H of finite energy, or even on more regular spaces, okay? Is invariant if it does not change under the action of the operator pt star. And this is the same, mathematically speaking, usually we use this definition, is the same as a measure mu. You see it appears in both sides, leaving the evolution of pt phi invariant, okay? There are a lot of papers. You don't find a list here because the list would be for sure too long and incomplete. Okay, many people gave contributions to existence and uniqueness of invariant measures. I put the linear process in this form. This is a particular setting, but just to understand the assumptions. We take the eigen values of the eigenfunctions of the Laplacian. We take this sequence, this form a complete orthonormal system. So we develop like a Fourier series representation of the linear process, and the sigma j are related to the space regularity. Okay, there are mainly two kinds of assumptions. One says that only a finite number of sigma j's are different from zero, finite dimensional noise. Okay. Suitably chosen as, if you want, we can speak longer, but I mean, you have to choose it in a suitable way. Huh? On the opposite side, you can take a noise which is full. Roughly speaking, sigma j decay with this power of with respect to the eigenvalues. Think of Q, the capital Q, which was the covariance of the linear process, as a negative power of the Laplacian, okay? And if you work on the torus, you have a lot of results. If you're not on the torus, you have something less, but never mind, okay? You can prove existence of invariant measure and uniqueness. I don't put assumption of F, it can be added, but this is the easiest statement, let me see, okay? What does it mean? There exists a unique invariant measure. This is ergodic, so the time mean converges to the spatial, let's say the statistical mean. It is even mixing, exponential mixing properties have improved. I mean, you have a lot of properties, okay? So which means that Navier-Stokes plus a noise is a good model to find an object, which is an invariant measure, unique, ergodic, and this is the basic statement in the turbulence theory by Kolmogorov. Okay, so the addition of a stochastic forcing term allows to use a mathematical machinery which is very powerful. But people dealt with different problems. Look, change a bit the dissipation in Navier-Stokes. Instead of putting a Laplacian, you put a power of minus Laplacian. Okay? When the power is more than 1, you call hypoviscous. When alpha is larger than 1, is a hyperviscous. You dissipate in a different way, okay? In dimension 2, always very easy model. Hypoviscous is more difficult, but anyway, let me say, roughly speaking, okay, you find the same result as for Navier-Stokes. Again, on the torus, there is a result by constating Latot's vehicle, and they proved that there is a capital N, depending on alpha, Q, and depends also on the viscosity. It's not written in the paper, okay? Such that if you put the noise in a sufficient number of directions, so sigma j are different from 0 for j from 1 till n, there exists a unique invariant measure. It is still ergodic, mixing, okay, and so on. So it means that you have a modification of a Stokes, and think of a hypoviscous case, which can be dealt with similar techniques. I mean, the result is the same, roughly speaking. Look at the parameter alpha. If alpha is larger than 1/2, the linear part dominates the nonlinearity. Here we have a minus delta to power 1/2 dominates the gradient here. So it is very similar to Navier-Stokes. However, for alpha smaller than 1/2, it is much more difficult, okay? We will keep in mind the two, both the two models. So Navier-Stokes and Navier-Stokes with fractional dissipation.
Sorry, so a half itself is fine, no?
Sorry, alpha?
Alpha equal to a half is okay, no?
No, I think this is a difficult one because they are at the same level of difficulty. So
then it's not dominating.
Yeah, exactly.
Okay.
Because think of this one, alpha equal 1, this is this part is the linear one, is parabolic. And so the nonlinearity says, okay, it's in a linear parabolic equation, but you have a lot of tools coming from the theory of parabolic equations. And when this does not dominate, it's a problem. They found that the parabolic nature of the equation says that even if you start with a condition which is only the space H2, it regularizes immediately, okay? And they were able to find the same property, okay, even for alpha, which is numerically, I think different alpha give a different dissipation. And usually in numerics, people take alpha larger than 1 to dissipate much more, okay? But even the other model is interesting, okay? The question is why there is ergodicity for every alpha. Let me make a short remark. This is our model. Viscous fluid with a stochastic force in term. Forget about the two red terms, you find Euler. Roughly speaking, because the boundary conditions are different, so this is true only on the torus. This is a mathematical simplification. So Euler equations have a lot of invariants. If you are in dimension 2, you have energy, entropy, or the Casimir, a lot, okay? And if you add to the unforced Euler equations some dissipation of this kind and some energy coming from a stochastic force in term, you expect that a balance can be reached, and the invariant quantities for the unforced Euler equations become something different. I mean, the invariant measures, okay, for the dissipative and stochastic model. This is the idea behind this one. Mathematically, you find the different difficulties, but the idea behind the model is the same. And so far we had alpha, which was positive. What happens when alpha is equal to 0? Is it possible to take alpha is equal to 0? What does it mean? There is no longer a Laplacian. This is just something proportional to you. So this is called the zero order dissipation. You put alpha equal to 0. It's called usually damping. Okay. So this is a different model. There is no longer parabolic structure. And we call them the damped Euler equation with stochastic force. And the idea, I mean, from the approach of the previous page, the idea is that you expect some invariant measures also for this model. What has been done was, first of all, existence of stationary solutions. Mathematically speaking, a stationary solution and an invariant measure are not the same object, because a stationary solution is a solution enjoying the stationarity. Okay.
So stationary solution, you of course mean a stationary process, right?
Yeah, you take the solution, ut defined for any positive t, okay? You take any subset, any at the time t1, t2, t3, okay? You shift. Instead of time t1, t2, t3, you evaluate time t1 plus h, t2 plus h, and so on. You have a finite dimension vector, and the two laws are the same. Okay. But if you want to speak of an invariant measure, you have to introduce the Markov semigroup, the PT you had before. So this is only a mathematical challenge. It's, from a physical point of view, a stationary solution is already a good answer, okay? But to speak of invariant measure, you have to introduce the Markov semigroup, and this is the difficult part, because you need, for people who knows Euler equations, Navier-Stokes are well posed in dimension 2 in the space H, the space V, whatever you want. I mean, it's enough to work with initial data of finite energy. However, for Euler, we require much more on the initial velocity. And so indeed, what we have to do is to work in this, the space L infinity for the vorticity. It will, it appears here. We write the equation for the vorticity, which is the curl of a velocity. It has a similar structure as before. Actually, it is very similar to a transport equation, but use unknown. We work on this equation. We found that we have a unique existence, a uniqueness of evolution in the space at infinity for the vorticity. And infinity is not a Polish space, it's not separable. And all the previous theory, you find a lot of results in the book by Zabchik, for instance. The previous theory requires the space to be a Polish space. So this is a problem from a mathematical point of view. But I revise with you shortly what is a technique called the Bogolyubov-Krylov technique to get existence of invariant measures. And we can see that changing a bit this technique, the classical technique set in Polish spaces, we can get the same result for Euler. Okay, here maybe I go a bit faster. So we have to modify the Bogolyubov-Krylov technique in order to deal with an equation set in the space L infinity. So what is Bogolyubov-Krylov? You take the Markov semigroup, defined as before, so statistical mean through observables. And if you are able to prove two properties, Feller property, which means that PT maps continuous function into continuous functions, which means, roughly speaking, it depends on the initial data. There is continuity with respect to initial data, roughly speaking, which is not unexpected, okay? And if you construct this sequence of measures, you take initial value, which is 0 for the initial measure, initial data, okay? You take the time averages, and if you are able to show some tightness, some compactness, okay, you can extract a subsequence whose limit is something fulfilling the relationship, which is the definition of invariant measure, okay? What we can do, we have to work in L infinity. We have to equip L infinity with the weak star topology. It's enough to speak of weak star topology, otherwise too technical. Because look, for Euler, there are no results with respect to the strong topology of L infinity. Anyway, L infinity is not separable, so it's not a Polish space. We found a good result in L infinity with a weak star topology, and that's enough. So from now on, for section number 2, damped Euler, we deal with L infinity with a bounded, we start topology. Now it's enough to speak of star topology, okay? And so we want to find Feller and tightness. Let me start with tightness. This one is, roughly speaking, a transport equation with a damping, okay? We can find estimates in LP and also in L infinity. And so we have good estimates with respect to L infinity. And this is exactly a tightness, because we have a uniform estimate with respect to an infinity norm. Tightness means you need some compactness, but balls of an infinity are compact with respect to the star topology, and so this is a mathematical result saying, okay, even if you have no Laplacian, you have only a damping term, let's say a zero order dissipation, and you can find a similar result to tightness. Okay. What about failure? Failure is something related to the continuity with respect to initial data, and again the weak star topology comes in. We can prove the failure property with respect to the weak star topology, roughly speaking. And what we need, let's keep it one, is also the Markov semigroup. I mean, you can define for fixed time the PS phi, but you have to show that it enjoys the semigroup property. And this one is another point where a modification of a classical proof of Markov property is needed, because Markov property is usually proved in Polish spaces. Okay, it's too technical. Let's keep it. Okay. So we are able to prove in a different setting, which is outside the usual Polish space setting, the two properties. I mean, there is a Markov semigroup which is, let's say, failure with respect to a weak star topology, and we have some tightness again with respect to weak star topology. And so by tightness, if we could use Prokhorov theorem, we extract a subsequence which is convergent, but there is a similar theorem in a non-metric spaces, which is a theorem by Jakubowski, and so we can apply the Bogoliub technique. So this is a result obtained with Akina-Bissell. So fix any positive damping. This is not the kinematics, this is positive, but it has the same role, and you find the existence of an invariant measure supported in the space an infinity, where we have to take the Borel subset with respect to the weak star topology. Okay, this is the first part. So a model for Euler where we introduce a damping and we add a stochastic forcing term can be treated in a way similar to the Navier-Stokes. That's the conclusion, which says again that you add a noise, some stochastic forcing term, and you have stochastic analysis, which is a good tool to find invariant measures. Anyway, the equation is a stochastic one. Now we change our subject. Look here, this is again Navier-Stokes. I go back to Navier-Stokes. You find the nu, which is the viscosity, the kinematic viscosity, you have a Laplacian, and we have a forcing term. But now we choose the forcing term with an intensity which is proportional to the square root of the viscosity. How much time? Minus?
You start to go minus. I mean, if you, I don't know how much.
Okay. Take mu equal to 0, you find again Euler, you are always on the torus. And the idea of fixing was to find what happens when nu vanishes, okay, in the limit. You expect to find something for Euler, but this is a deterministic unforced Euler. Deterministic unforced Euler can be studied with deterministic tools, but you can be interested in finding stochastic processes solving it, even if there is no stochastic forcing term, okay? And this is a technique. Coxin realized that you can find a limit when the viscosity vanishes, and the limit is not the zero process. Look, you write down Ito formula for the L2 norm of the velocity and the L2 norm of the verticity. You have here, there is something related to the square of this quantity, so there is nu. For a stationary solution, these two terms vanish. You find something which is independent of nu, and you have some uniform estimates for any positive nu, roughly speaking. And what is important, you have this, the second relationship, which says two things. First of all, that capital U is not the zero solution, it's not the zero solution of Euler. The zero solution is a solution, because there is no forcing term. And the second, that the limit keeps track of the intensity of the noise. Let's say little q is the trace of the capital Q, which was the covariance of it. And change the noise, you find a different limit. Okay. Can we do the same? Changing the dissipation. This was a result by Cookson. What I did is to repeat the argument by Cookson, changing the dissipation. Okay. And the result, I provide you all the result because it's too late, sorry. You can do for hypoviscous, hyperviscous, okay? The two results are different. Let me state only for hypoviscous. Fix any power alpha smaller than 1, and you find something similar. Focus on relationship number 5. Again, the limit is not the zero process, it's a stationary process, solving deterministic Euler equation without forcing term. It depends on alpha and it depends on Q. The fact that it depends on alpha requires an assumption of the noise. The noise must act on at least 4 suitable directions. The sigma j appeared before, okay, at least j should be chosen in a suitable way, okay? And they are really different. So the question is, the answer is, the conclusion is that for Euler, by means of stochastic analysis, you can find a lot of stationary processes solving the deterministic unforced Euler equation, and they depend on the approximation through the noise and through the kind of dissipation, let's say the power alpha. Okay, that's all. Sorry for today.
Thank you very much. Yeah, Michael.
Yes, thank you for your talk. Like in the hyperviscous limit case for alpha greater than 1. So in the implicit, the zero noise limit, you get like you mentioned stronger solutions, stronger results. But what are the type of these stronger results?
The limit has such a regularity that you arrive in the class of solutions where you have existence and uniqueness. You can define the Markov semigroup. You speak exactly of invariant measures. If alpha is smaller, the limit is less regular. You have only stationary solutions. But I mean, for alpha larger than 1, you get exactly the same as Cook's. This is an invariant measure. Okay.
This is the invariant measure because for instance, in classical simulation of turbulence 2D, when we go to turbulent regime, it's classical to add like a hyperviscous term.
So alpha larger than 1.
So, yes, so that's why.
Because it converges faster, I think.
Yes.
Okay. You dissipate faster.
You dissipate faster, you get to you get like to statistical equilibrium faster. So that's
the result by Cookson, alpha equal 1. Translates easily to alpha larger than 1. Okay. If you're in 3D, you can do something for alpha much larger than 1. Okay, so that's why I focused on 2D, because people studied also the hyperviscous in 3D because
yes,
for alpha, I think larger than 5/4, you find existence, uniqueness, and you repeat what to do for naviscous in 2D. Okay, but usually mathematically we say it's too easy, okay?
Yeah, the difficult case is for alpha less than 1.
Exactly.
Peter.
Somewhere midway through your talk, you seem to make the point that when you have deterministic dynamics with some invariants, like the Euler equations, and you add fluctuation dissipation, that gives rise to existence of invariant measures. How general can you make this statement? Is there a high-level abstract statement which allows you to, take the beginning part as assumptions and infer the existence of invariant measures? Is there something of that sort?
The answer is yes for Navier-Stokes, but we are asking for a general PDs, okay? I think, no?
PDs or not even PDs, but general dynamical systems.
Because wait, the part number 3, let's say, debated by Cookson, works because you have some Hamiltonian structure. So you need 2 invariants. This is really a result only in 2 dimension for 2-dimensional Euler. However, for the other damped Euler, for the hyperviscous Navier-Stokes, you can deal also with a 3-dimensional case. Okay. So the idea is that you take Euler, which is in a Hamiltonian structure, you have some invariants, and adding a dissipation and some energy, they reach a balance, but think of the linear part, forget the non-linearity. So forget Euler, okay? Take a Stokes problem, and if you are able to find the result for the linear problem and the non-linearity is dominated by the linear part, alpha equal to 1, for sure you can get the result. Okay.
So you're going through some Ornstein-Uhlenbeck kind of instruction.
So for sure, if how to say, if the linear part dominates, is trivial. If alpha is smaller than 1 alpha, I don't know. For Navier-Stokes it works, and it has been much harder. In general, maybe yes, you have to try. Depends on the non-linearity, yeah, roughly speaking. Okay.
Yeah, please.
Maybe my question is very stupid and naive, but I would like to ask you, is there some physical meaning of taking the damping term, or it helps in the LP, L2 estimate, because usually it helps to close the estimate, but I don't know.
Damped Euler appears in a book by Gallavotti. So there is a physical interpretation of the damping term. Okay. There are also models for Navier-Stokes, so you have still the Laplacian, okay, and also a damping term. And again, people from a physical point of view, they introduce some damping term. I'm not an expert, so I think I can give you some references. Okay, damping term is not only the limit from the mathematical point of view. Okay, it appears also in some physical model. Okay.
Can you say more about the 4 magical modes?
Ah, sure. Martin and Perdue,
yeah,
they studied the 2-dimensional Stokes, and they realized that they are on the torus. You fix the eigenfunctions of the Laplacian. Okay. The noise has to act in at least in 2 directions, in such a way that the non-linearity sees the noise and transports the noise in all the directions. This is the action of the nonlinearity. So they made a deep analysis of nonlinearity, U gradient U, okay, and they realized that if you have a noise only in particular directions, the noise is not spread out. Right? In other directions, you bring the noise.
Yeah, that's the Ormondel condition, right?
Exactly.
So to have the Ormondel condition, what I want to understand is like the 4 modes. They are like with low wave numbers, or it's a mixture of like.
No, it's enough to have at low wave numbers, but chosen in a suitable direction. Okay,
like linear combination of the eigenmode, or just like 4 particular eigenmodes?
May I?
I think it's 4 particular modes.
No, let's wait. Before I read, so you had some eigen. Let's see. How to summarize it shortly? All the direction can be labeled in this way, okay?
Yeah.
And now you are in dimension 2, and you put a subindex, which is a vector of the lattice Z2, okay? It is enough to take one here and another one there. Okay, this is a k equal to 1, 0 and k equal to 1, 1, okay? You have to take also the opposite ones because you need some real object. These are the 4 modes, okay? But if you take, for instance, 4 modes in this way, that one, that one, that one, and that one, it does not work. Maybe it's technical, but just to say, they understood how the noise acting only on a few directions, okay, is transported by means of nonlinearity.
To get the regularity of the invariant measure, for instance, the mu, like, you know,
to get uniqueness.
Uniqueness.
So the solution lives in the full space. Okay. Otherwise, there are some spaces of this space here which are invariant. Okay, and invariant, and you activate on few modes, and so you find nothing interesting. You have to mix up the dynamics.
Okay, so let's thank the speaker. And the next speaker is Francesco Grotto. Yeah, okay. So I'll just go like this. Yeah, cool. Okay.